Here are some points around a circle, and these look kind of randomly spread. They don't appear to have any structure. But this collection of points does have some nice properties. First, it is buildable, which means that it can be built using regular polygons. So, we start with a regular pentagon. We place the points at its corners, and then we add this regular heptagon, and then this regular two-gon, just two opposite points. And now we notice these 3 points are all in our regular triangle, so we can subtract them. And now the resulting collection of points matches what's on the left. We just built it using regular polygons. This set of points also has the property of being centered, which means the average point is the center of the circle. And it's centered because it's buildable. Looking back through the build, we started with a regular pentagon, and these 5 points are evenly spread, so they average to the center. And then we added a heptagon, which also averages to the center, so adding this didn't change the average. And the same thing with the two-gon. And then the triangle, again, didn't change the average. So at the end, we're still left with something centered. And this holds in general. Anytime that we're adding and removing regular polygons, we won't be changing the average. So every buildable collection is centered. If we're able to build it, it will have the average as the center. And this was the topic of my last video about buildable collections, but it relied on a big assumption. It would maybe be better to say every finitely buildable collection is centered, because we're assuming that we have some list of steps where we're adding and removing regular polygons, but eventually we stop. Eventually we're done. There's only finite steps. But what if we allow a build to have infinite steps? What are we able to build? Will they always be centered? Before we start, we need to be careful. Anytime we're working with an infinite set of operations, we want to be careful about how we interpret the result. Let's look at this build, for example. We add a triangle, and then we remove that triangle, so the points go away. And then we add the same triangle, and then remove the triangle, so the points go away. And we keep repeating that. We go back and forth between having 3 points and having 0 points, so it's unclear what the result should be. And maybe it's best if we just don't allow this kind of build. And a big reason for that is the order of the steps. Going back to our starting shape, we built it using a pentagon, then a heptagon, then a two-gon, and then removing a triangle. But what if we change the order of those steps? Maybe we start with the two-gon, then add the heptagon, and then remove the triangle, which leaves us with this kind of negative point, and then we add the pentagon. So the resulting set of points is the same. The order of the steps shouldn't matter. But now, going back to this build of infinitely adding and subtracting triangles, here we go back and forth between having a triangle and being empty. But we could rearrange these steps to be add, subtract, going on forever. And here, we steadily accumulate more and more and more points. But we could again rearrange to be subtract, add. And here, we're gradually accumulating negative points. So reordering these steps creates a problem. So we don't want to work with this kind of build. To prevent this, let's make a definition. A point converges if it is in a finite number of steps of a build. It's in a finite number, which means there is some last step that it appears in, and after that, nothing changes with that point. The coefficient is fixed for the rest of the build. And so these points are safe to work with. In the example we just worked with, none of those 3 points converged because they were in every step. Okay, so we like converging points. We'll say that a build converges if all points within the build converge. So we can interpret the results nicely. So with these definitions, we can now use some builds, and we could do something like this. Place 2 opposite points, one of them being halfway around the circle, and then again with 1 being a third, and then again 1 being a quarter of the way around the circle, and then a fifth, and then 2/5. And if we could keep repeating this process, we eventually get every point that's a rational distance around the circumference. And this is something we couldn't do with the finite build, because there are infinite points. We can't place infinite points in finite steps. But we notice this collection is centered. Can we make something that's not centered? Turns out we can. Not all infinitely buildable collections are centered. And a great example of this is this collection. This is infinitely buildable, just 1 point. So how do we do it? Well, we add a line through that point. And now we have an extra point, so we will subtract a triangle to get rid of that point. But now we have 2 negative points that we don't want, so we will add pentagons to cancel them out. But now there's a bunch of positive points that we don't want, so we will subtract 7 gons to cancel them out. And you may see where this is going. We will then add 11 gons, subtract 13 gons, add 17 gons, and continue on forever, gradually increasing the primes. And because we're using a different prime every time, we're never repeating a point. So this point appears only in the first step. So it ends up being in the collection. Every other point appears in 1 positive step and 1 negative step. So the positive and the negative steps cancel each other out, and the point is only in 2 steps, which means it converges. So we're left with just 1 point. And because we know how to build 1 point, that also means we can build pretty much anything that we want. In my last video, I gave this as a counterexample. This is centered, but not finitely buildable. But this is infinitely buildable. If we label each of these points, A, B, C, D, and E, we can create each of them separately, mimicking the 1-point build from before. So we have a build of A, which is just a rotated version of that 1-point build, and then a build of B similarly, and C and D and E. And so to build the collection as a whole, all 5 points, we just step through the first step of each build, and then the second step, and then the third step, and the fourth step, and continue on like this. And every point shows up maximally twice in each of these builds, which means that each point shows up maximally 10 times in the total build, which means each point converges, and we get the resulting collection that we want. Now, we did this with those 5 points, but we could do that with any points. Every finite collection is infinitely buildable. We can build all the points separately and then add them together like we just did in the example. But what about collections with an infinite amount of points? How do we deal with that? Well, it depends on the kind of collection. So first, let's look at countable collections with finite coefficients. So we have some infinite collection that we have the points all listed out, and each of them has finite coefficients, which means each point only appears a finite amount of times in this list. Now we can take each point separately and create a build, just like that 1-point build. But now we have a slight problem, because no point can be in all of the builds. Otherwise it wouldn't converge. And because we're not being careful about how we make these builds, that might happen. But we just have to tweak things a bit to avoid this problem. Now, the technique for the 1-point build used primes. We added a 2-gon and then subtracted a triangle, then added pentagons, subtracted heptagons, and so on. But we didn't need to do it exactly like this. We didn't need to hit every prime. We could have instead maybe skipped every other one, 2 gons and then 5 gons and then 11, 17, and 23. And we don't even need to increase the primes. We could start with 7 gons and then subtract triangles and then add 19 gons. All that's really important is that we have some infinite amount of primes that we're using. We can skip over any that we want, we just need an infinite amount. So to construct our collection, we'll list all of the points here, and we'll start with the first one, a sub 1, and we can put down a 2-gon to get that point. Now for a sub 2, we will also put down a 2-gon, unless the other side of the 2-gon, that's not a sub 2, has already been used. Then we don't want to use it, and we'll use a triangle instead. Then we go up to a sub 1. We've already used a 2-gon for a sub 1, so maybe we subtract a triangle, unless that hits a point that already exists, and then instead we'll subtract a pentagon. And then down to a sub 3. Maybe this time we can use a line, and then go up to the next step of a sub 2. Maybe we need a 7-gon, and then a sub 1, maybe we need a 7-gon again. And then we start at a sub 4, where maybe we need a pentagon, and then an 11-gon. And so we continue this process. We travel diagonally across the points, so we will eventually hit every single step. And at each step, we add a shape of the lowest prime that won't hit any existing points. At any stage in the build, we only have a finite amount of existing points, but there are infinite primes, so we will always be able to find the lowest prime. And doing this means that each point will only get hit twice during this build. So this means that for some a sub k having a coefficient c sub k, a sub k appears in it at most the absolute value of c sub k plus 2 steps. The absolute value of c accounts for how many times it appears in that list on the left, and then the plus 2 accounts for how it may be used in the middle of some construction to be added and subtracted. But we're always checking to only use new points, so each point gets used maximally twice during this step. And so this means that every point converges, since the absolute value of c plus 2 is always finite. So every countable collection with finite coefficients is infinitely buildable. We can have any amount of points that we want as long as there aren't an infinite amount stacked at the same location. But what if we want to stack infinite points at the same location? For example, maybe we want infinite copies of this point and nothing else. Can we build something like that? Let's go back to this build of repeatedly adding and subtracting a triangle. We decided this was problematic. But what if we only have adding triangles? This doesn't converge because the coefficient of each point steadily increases, but we can kind of understand what the result will be. It will just be an infinite amount of copies of each of those 3 points. And we can rearrange the steps however we want, and we'll still get the same result. And we could even throw in 1 or 2 subtractions of the triangle, or even any finite number of subtractions of the triangle, and we'd still get the same result. And kind of the opposite, we could also infinitely subtract the triangle and get infinite copies of negative versions of the points. So it seems like maybe we want to be allowed to do this kind of construction. So how do we think about this? Well, let's make a table. If a point appears a finite amount of times in a positive shape and a finite amount of times in a negative shape, it will have some finite coefficient. And that's good, that means it converges. We've already dealt with that. If it appears an infinite amount of times in a positive shape, but only finite amount of times in a negative, maybe we'll say it has infinity as a coefficient. There are infinite copies of that point. Now, if it appears finitely as positive, but infinitely as negative, we can say that it has negative infinity as a coefficient. There are infinite copies of the negative point. The only problem comes when we have infinite of both. And we saw this before with repeatedly adding and subtracting the triangle. So we'll say that this kind of point is conditional, because whether it stays at 0 or goes off to infinity or negative infinity depends on the order. So we'll redefine, we'll say a build converges if none of its points are conditional. And using this new definition, it's pretty straightforward to update our techniques from before to allow for infinite or negative infinite coefficients, which means every countable collection is infinitely buildable. We can do pretty much anything we want as long as we have at most countable points. And this is exactly where we draw the line, because no uncountable collection is infinitely buildable. And I'll leave that to you to think about why not.